We're going to take a look at a problem using radioactive gold, which is used in imaging the structure of the liver. It is known that radioactive gold has a half-life of 2.67 days. We're going to start with 50 milligrams of the isotope, and we want to know how many days will it take for this patient to be down to only 5 milligrams of the isotope in their body. So when I go to do this problem, first thing I want to note is any keywords, and I picked up on half-life. So that gives me a good idea of which equation to write. So in my pre-lecture notes, I have half-life model, population based on time is the starting amount. I use 0.5 as the base because of the half-life, and I use an exponent, the time, divided by that time it takes to decrease by half, or half-life, d. So I'm going to worry about just this first bullet point for the first problem, and then we'll come back and take a look at the second problem based on the same scenario. So what I want to do is I want to take this generic model that I have from my pre-lecture notes, and I want to fill in as many numbers as I can based on the problem. So let me move things around here so that I can potentially get just a little bit more space. Here we go. And I'm going to get a darker pen color if I can. All right. So in that model, P of t is the population at some point of time. P0, starting population, 0.5 is part of the formula, T over D. So going through here, it says if we start with 50 milligrams, so I know that that is my starting population, 50, put that into my formula. How many days, so that's my question, how many days will it take till they have only 5? So 5 is the population at a later point in time. 0.5 is in my formula. T represents how many days, the time, that's the question, so that stays as a variable. And D, the half-life, is given to me up here, and so I put in 2.67. So this is the equation that I'm going to work with a goal of figuring out time. So in order to try to get time all by itself, first thing I'm going to do is move the 50 to the other side. Right now it's being multiplied, so I'm going to do the opposite, which is divide on both sides. These guys cancel. So 5 divided by 50, my calculator tells me 0.1. And this side, I don't need quite as many parentheses anymore because I have taken care of this by division. So I still have exponent t over 2.67. Now, like we've done before, this problem contains an unknown exponent. And so the inverse, the way to figure this out, is to change the whole problem into exponents by using a logarithm. So on my left-hand side, I'm going to write log of 0.1 equals log of, and I write this whole thing, parentheses 0.5 with an exponent of t over 2.67. And then we have our product property, which says once you've changed this into exponents, which we've done by using logarithm, we will take this and turn it into a multiplication problem by moving it into the front. So I'm going to put this on my calculator so that I have a number to deal with rather than keeping to write that. So I type on my calculator log of 0.1 and I get a value of that of -1. And that actually makes sense because 0.1 is 1/10, so that would be 10 to the -1 power, and we know that logarithms give us the exponents for a base 10. On this side of my equation, I have changed this into a multiplication problem, so t over 2.67 is now multiplied by log of 0.5. And I would really like to have a decimal here instead of this word, so I'm going to put that on my calculator. -1 equals t over 2.67 times, I type this on my calculator and I get -0.3010. And we talked about before that we want to keep at least 4 digits in that decimal. So in order to solve this equation, I need to get t all by itself. It has a number divided and multiplied. So I'm going to multiply on both sides times 2.67. And on the side of the equals. Over here, these guys cancel out. And here, this is multiplication, so I get negative 2.67 is equal to t times negative 0.3010. So to get t by itself, I do the inverse, so I'm going to divide by negative 0.3010, divide by negative 0.3010. These guys cancel. And so I'm left with t, the time, is equal to 8.87 on my calculator. And so I went with approximately 9 days. There are no rounding rules to memorize. Follow the directions in your homework as far as rounding. So you'll remember that this problem had a second half. So we know the answer to the first half of the problem. It would take 9 days until this radioactive gold would reduce to just 5 milligrams with this procedure. So the next half of this problem says if the doctor needs the patient to eliminate at least 65% of the med before running another test, how many days will the patient need to wait before having the next test? So remembering my original equation from originally reading this, we knew that there was a half-life model, starting amount, and then we used the 0.5, and we had t, the unknown time, and we knew that it took 2.67 days for it to decrease by half. So we really have to think about what all these variables mean when we're working with the need to eliminate 65%. So when we think about the starting population, that would equal 100% of what the patient was given. That was everything they were given. So eliminate, that sounds like subtraction. We need them to get rid of 65%. So this is what they're eliminating. And that would give us 35%, and that is what would remain. So in this formula, the P of t over here, this variable, the whole thing, is representing a population. Well, a population equals what exists, so it equals what remains. So when I go to fill in numbers, I find it easiest to work with this problem in percents because it was in percents. So for my P0, just like we set up here, P0 was 100%. So I'm filling in 100 where the P0 is. I have that it had the half-life, so the 0.5, and I have my exponent t over 2.67, and my exponent has that t in it because the question here is how many days. So over here where P of t was, that is the population that remains, so that's where I'm going to put my 35, representing that they were at 100% and they went down to 35%. From here, the math is very much like it was in the previous problem. So I start by dividing by 100 to try to get t by itself. So this is always my first step, is dividing by that initial population. These cancel. And I have 0.35 is equal to 0.5 with an exponent of t over 2.67. In order to continue, I need to take a logarithm on both sides. So I take the log of 0.35, and I'm just writing this out so you see exactly what I'm doing, and I put the word log on this side as well, of 0.5 with an exponent of t over 2.67. On the left-hand side, log of 0.35, I'm able to type that in my calculator, and so I got a negative 0.45 and I'm keeping that to 4 digits. And then on the right hand side, I'm going to take this exponent, this whole piece, and I move it down to the front, and it becomes multiplication, and that's all based on the product property. And so we have this over 2.67, and that is times the log of 0.5. And so then my next step is to figure out what is the decimal for log of 0.5. So negative 0.4559 equals t over 2.67. And I'm typing on my calculator log of 0.5, and I get negative 0.3010. So now I have a little bit of work to do in solving this. And so what I want to do is get rid of this number in the denominator. That's division. So the opposite would be to multiply by 2.67 on both sides. I'm going to use parentheses here. So this decimal times 2.67. Over here, these guys cancel out. Over here, I'm going to take 2.67 and multiply on my calculator. And when I did that, I had a value of negative 1.217. I didn't write the rest of it down. And so what I have left over here is t times negative 0.3010. So to finish out the problem, I will divide by the negative 0.3010 on both sides of my equation. And so that allows me to solve that t is equal to, and I type this on my calculator, and I got very, very close to 4. So going back to the question, this would tell me that the patient needs to wait at least 4 days. And that way, during those 4 days, their body would eliminate 65%, and they would have only 35% remaining.